These are the notes for AP Calculus on the topic of differentiating and integrating natural, exponential, and logarithmic functions. So let's first review what the natural exponential function is. So the natural exponential function is in the form f of x equals e to the x. And remember, e is a constant that's approximately equal to 2.718, and it keeps on going with no pattern to it. It's an irrational number, kind of like pi. And it's one of those constants that comes up a lot in math and science. So it's actually referred to as Euler's constant. And because of that, it's assigned a lowercase e to represent it because it's used so frequently. And then the natural logarithmic function is the inverse of the natural exponential function. It's written as f of x equals the natural log of x. But remember, natural log of x is a shorter way of writing log base e of x. And the natural log, in addition to the common logarithm with a base of 10, are the two most frequently used logarithms in math and science, and hence you'll see on scientific calculators, those are the two log buttons that are on there. Log base 10, which is the base is not written, and the natural log. So let's take a look at how we take the derivative of, or differentiate, a natural exponential function. So remember, this notation here means you take the derivative, d over dx, of whatever's inside. The derivative of e to the x is e to the x, which may seem kind of strange. Why does it stay the same? Well, let's take a look at the graph over here to see why that is. Here's the graph of y equals e to the x. So if we look right here at the point 0, 1, you can see when you plug in 0, you get a y value of 1. E to the 0 is 1. That's the y value. And remember, what the derivative represents graphically is the slope, or the slope of the tangent line. So if you're thinking about the tangent line that goes right here, this tangent line would have a slope also of exactly positive 1. And that's not true at just this point. It's true at every point along the curve. For instance, if you plug in 1, you get e, or about 2.7. And the slope of the tangent line right there is also exactly e, or 1, or 2.718 approximately. If you plug in negative 1, you get 1 over e as the y value. And the slope of the tangent line is also exactly 1 over e. So that's why the derivative is the same as the original function, because the value of the natural exponential function, or the y value, is also its rate of change or slope. At every point along the curve, the y value and the slope are identical. So it has that special property. So the derivative of e to the x is just e to the x. So now let's take a look at some example problems. It says find the derivative of the function. So f prime of x, the notation for the derivative. Remember, when you have a constant out in front, when you take the derivative, that constant just stays there. And then the derivative of e to the x, we just learned, is e to the x. So this one looks identical to the original function. The next one, though, is not quite as simple. When we take the derivative of this one, f prime of x, the difference is it's not just e to the x, it's e to the negative 3x. So that's negative 3x. That's like a function inside, which means we have to use the chain rule. So when you take the derivative of e, just like e to the x, that part's going to stay the same. So e to the negative 3x, that doesn't change when you take the derivative, just like e to the x doesn't change when you take the derivative. It stays the same. But because we need the chain rule, remember the chain rule says when you have a function inside, in this case negative 3x, we have to multiply by its derivative. So the derivative of negative 3x, remember, is negative 3. So it gets multiplied by negative 3. So whenever the exponent of e is not just x, then you're going to have that function inside, and it's going to require using the chain rule when you take the derivative. All right, let's take a look at the next one. We've got y equals e to the x squared times the square root of x. So this way a little more here. Let's first rewrite this one, so it's easier to take the derivative before we do so. So we've got e to the x squared. So x squared is the exponent, times square root of x, but that's the same as x in fractional exponent form, to the 1/2. So here, to take the derivative, which in this case, since it's y equals, is going to be written as dy dx. Overall here, we've got e to the x squared times x to the 1/2. So overall, we're going to have to use the product rule. We have two functions multiplied together that we're trying to take the derivative of. And remember, the pattern in the product rule says you take the derivative of the first one times the second one as it is, plus the first one as it is times the derivative of the second. So let's start with the derivative of the first one, and that's going to require the chain rule because, again, we don't have just x as the exponent, we have x squared. That's our function inside. So using the chain rule, the derivative of x squared is 2x. Multiply that, and then e, if you take the derivative of that, remember that's the part that stays the same when you take the derivative. So that e to the x squared stays the same. So that's the derivative of the first one, using the derivative of e stays the same and the chain rule. The derivative of the first one times, remember the product rule says the second one as it is, which in this case is x to the 1/2. And then plus the first one as it is, e to the x squared, times the derivative of the second one. You're just using the power rule on that. The derivative of x to the 1/2 will be 1/2 x to the negative 1/2. Now let's see what we can do to simplify this a bit. So if we had to work with this, if we had to find our increasing decreasing intervals in the first derivative or relative minimum axis, if we left it in this form, it would be pretty tough to do that. So what we can start to simplify is by looking for the GCF, the greatest common factor. So if we think of this as all multiplied together, that's like our first term. Plus, these are multiplied together, that's like our second term. So what do those have in common we could factor out as a GCF? Well, you can see they both have e to the x squared. So we can take that up as part of our GCF. And this one has x to the 1/2, this has x to the negative 1/2. So you can factor that out by factoring out the lower exponent, which in this case is x to the negative 1/2. And that's all they have in common, so let's put in parentheses what we have left. Okay. So let's see what's left of this first term. Well, we still have the 2 and the x. We didn't factor those out. E to the x squared we factored out, so that's gone. And then we had x to the 1/2, and we factored out x to the negative 1/2. So to see what's left there, it's going to be x to some exponent. We can think, well, if we were to distribute this back, right, when you multiply the x's, you'd have to add up the exponents, right? So negative 1/2 plus this exponent would have to equal 1/2. And what would you add to negative 1/2 to give you positive 1/2? That would be 2/2. So if we put in 2/2 there, that would be correct. Okay. But 2/2, 2 divided by 2, that's just 1. So it's simpler to just write it as 1. Now you can see if you multiply that, x to the negative 1/2 times x to the first, you'd add the exponents, 1 and negative 1/2 would give you back a positive 1. And then plus, let's see what's left of this term. Well, we factored out the e to the x squared. We didn't factor out the 1/2, so that's still there. But we did factor out the x to the negative 1/2, so that's gone. So all that's left with that one, second term is just 1/2. And now there's just one more thing we can do to make it a little bit simpler. And that's dealing with that negative exponent. Now that we have it factored out, we can move it to the denominator. You could write it as x to the positive 1/2 when you move it there. But if we switch that to radical form, that's the same as the square root of x. And then if we just simplify what's left in the parentheses, 2x times x to the first, that's like 2x times x gives you 2x squared. And then plus 1/2. And now, if you were to need to find the increasing decreasing intervals, or you needed to find relative minimums and maximums, now you can work with this more easily by setting the numerator and denominator equal to 0, and then testing your number line to see where the first derivative is positive and negative. So that's the simplified form of our derivative. Okay, now let's take a look at some integrals. So we just learned that the derivative of e to the x is e to the x. Well, that means if you reverse that, if you integrate e to the x, it's just going to give you e to the x also. The only difference is if it's an indefinite integral, you need to add that unknown constant plus c, because the derivative of any constant is 0, so you could, when you integrate, you could have any constant added there. So let's look at some examples here. If you integrate 6e to the x, well, just like taking derivatives, when you have a constant out in front as a coefficient, that constant just stays there. And then we just learned, when you integrate e to the x, you just get e to the x. But since it's an indefinite integral, it doesn't have a lower and upper limit, you need that unknown constant plus c. But the next one's not quite as simple because it's got 3x e to the x squared. So you can't integrate it in this form, it's too complicated. So, to try to make it simpler, remember the technique we use is called u substitution. And usually what you say u equal to is a function inside. In this case, you can see the function inside is actually x squared. So if you say u equal to x squared, now we can rewrite this as the integral of 3x, that's still there, but now we can write it as e to the u, since we said u equal to x squared. But remember, we want to get it all in terms of u, so we need to replace the dx with du. And the way we do that is by taking the derivative of what we say u equal to. So the derivative of x squared du dx is 2x. And then when you multiply both sides by dx and divide by 2x, you end up with dx equals du over 2x. So that's what's going to replace the dx right there. Instead of dx, we have du over 2x. And now let's see what simplifies there. Well, you can see the x's will simplify out. And then you can pull out a constant of 3/2 outside the integral. Remember, constants you can pull outside the integral and multiply that. And then all that's left is e to the u du. So all the x's canceled out, reduced out, and now we can integrate something simpler than what we started with. So we have 3/2, and when you integrate e to the u, you get e to the u. Just like when you integrate e to the x, you get e to the x. But again, it's an indefinite integral. There's no lower and upper limits. So we need that unknown constant c. But there's one more thing. This is not quite our final answer, because notice our original problem is in terms of x. So our final answer, when you integrate, also needs to be in terms of x if it's an indefinite integral. So the way we do that is, remember, we take what we said u equal to x squared, and substitute that back in as our last step. So we have 3/2 e to the x squared, and then plus our unknown constant of c. So we've taken a look at two indefinite integrals using this formula. Now let's take a look at a definite integral. In this case, from 1 to 2. You can tell it's definite because it has lower and upper limits, as opposed to the indefinite ones do not. So, again, you can see this is way too complicated to integrate in this form. So again, we need to try to use u substitution to make it simpler. And in this case, the function inside the exponent, we've got x squared minus 1. So let's set u equal to that. But since it's a definite integral, we also need to convert our lower and upper limits to be in terms of u. We need the whole integral in terms of u. So let's go ahead and substitute in 2 for x. So we get u equals 2 squared minus 1. Well, that's 4 minus 1 gives you 3. So when x is 2, u is equal to 3. So our new upper limit becomes 3. And then when you substitute in 1 for x, you get 1 squared minus 1. Well, 1 squared is just 1 minus 1 gives you 0. So when x is 1, u equals 0. So now our new lower and upper limits are from 0 to 3 in terms of u instead of 1 to 2 in terms of x. And then we still have the x there. But now we can write this as e to the u, since we set that equal to u. But again, we need to get it all in terms of u, so we need to replace the dx with something involving du. And the way we do that is by taking the derivative. Du dx, the derivative of x squared is 2x, the derivative of negative 1 is 0. And then just solve it for dx. So after you multiply by dx and divide by 2x, you get dx equals du over 2x. We can take that and substitute in there for dx. And then you can see the x's reduce out. You can pull out the 1/2. And then what we're left with is e to the u du. So we have 1/2. Again, when you integrate e to the u, that just stays the same. That's e to the u. But remember, on a definite integral, you don't need a plus c, because when you plug in the upper and lower limits, the c's are going to cancel out every time anyway, so it's not necessary. And remember, the way you write it after you integrate it with a definite integral, got a little line here from 0 to 3. And remember, to make it easier to work with and keep that constant separate, you can turn that into brackets there. You can see what you're really substituting to more easily. But remember, on these, unlike the indefinite integrals, you do not plug x squared minus 1 back in for u. The reason why is we've already converted our lower and upper limits to be in terms of u, right? Because the whole integral had to be in terms of u for it to make sense. So because of that, these are in terms of u, we're going to plug them in for u, not for x. So on the outside, we've got 1/2. And then we'll substitute in 3 for u, so it'll be e to the 3rd. And then we always subtract, and you plug in the lower limit, which is 0 for u. So we have 1/2. E cubed, that's just about close to 2.7 cubed. You can just leave it in terms of e minus e to the 0. Remember, any base other than 0, raised to the 0 power, is just 1. So 0 to 1. So you could leave it like that, or if you want to write as a single fraction, you could write it as e cubed minus 1 all over 2. So with a definite integral, we get a definite number as our answer. No plus c on these. So because e cubed, that's about 2.7 cubed minus 1 divided by 2. Now let's take a look at another formula for today. Actually, two that go together. And that's the derivative natural log of x and the derivative natural log of the absolute value of x. So the derivative natural log of x is 1 over x. The derivative natural log of absolute value of x is also 1 over x. Notice there's no absolute value signs in the derivative here. They're both 1 over x. The only difference between these two is the domain. So the domain of any logarithm, including the natural log, which is log base e, remember the domain of what can go inside here, because it's the same e to what exponent gives you this. Well, e to an exponent is always going to give you something positive. So you can only have positive numbers inside there, inside the logarithm. So the domain, one way to say it, you could say the domain is x has to be greater than 0. Or in interval notation, that would be from 0 to infinity. Whereas on the natural log of absolute value of x, that absolute value changes negative numbers to be positive. So now we can plug in negative numbers. And that will be okay because of the absolute value signs. However, there's still one number we can't plug in, and that's 0. Because even when you take the absolute value of 0, that's still 0. It's still not going to be positive. So now the domain would basically be all real numbers except 0. In other words, x cannot equal 0. Or in interval notation, that would be the interval from negative infinity to 0. U, the interval from 0 to infinity. So keep that in mind when you're taking the derivative, because the derivatives look identical. On this one, you can plug in any number except 0, which the derivative really already shows you, because you can't plug in 0, it would be undefined. But with this one, you have to be careful because it looks like you can plug in negative numbers into the 1 over x, but you have to remember where it came from is the natural log, and the domain was only positive numbers, so even though it doesn't look like it, that means you can only plug in positive numbers in the derivative if the original function didn't have the opposite value. Alright, so now let's take a look at some example problems using these two formulas. So let's take the derivative of each of these functions. So since it's y equals, we'll write the derivative dy dx equals the derivative natural log of x cubed. Well, the derivative natural log of x is 1 over x. But here, it's not just x, it's x cubed. So when you have a function inside, again, that's going to require using the chain rule. And the chain rule says you have to multiply by the derivative of that function inside. But let's start with the outside function. Normally, derivative natural log of x is 1 over x. But here, it's not going to be 1 over x. It's going to be 1 over whatever's inside the logarithm. In this case, it's x cubed. But then the chain rule says you multiply that by the derivative of the function inside. The derivative of x cubed is 3x squared. And then when you simplify that, you're left with 3 over, you can see, 2 of the x's reduced out, so you're just left with 3 over x. That's your derivative. Now let's take a look at the next one. On the next one, we've got f of x equals 5 natural log of x cubed. So notice this time, the function inside is natural log of x. That's inside the cubed. So again, we will still need the chain rule because there's a function inside. But when we take the derivative this time will be written as f prime of x. On the outside, we're going to use the power rule since this is cubed. So the power rule for derivative says you bring down the exponent and multiply it out in front times 5 times the 3 gives you 15. And then you reduce the exponent by 1, so now it becomes natural log of x squared. But then the chain rule says you have to multiply by the derivative of the function inside. And the derivative of natural log of x, we just learned, is 1 over x. So here there's not really that much to simplify. If you want to write it as a single fraction, then you could write it f prime of x is 15 times the natural log of x squared, all divided by x. On the next one, we've got g of x equals natural log of the absolute value of the sine of e to the x. So here, when we take the derivative, g prime of x, we've really got the double chain rule because we have 2 functions inside. So notice on the outermost function, we've got natural log. Inside natural log, we've got sine. And inside sine, we've got e to the x. So remember, when you use the chain rule, you always start on the outside and work your way. Like on this one, the outermost function was natural log, so we start with the derivative of that. On this one, the outermost was this to the 3rd power, so we start with the power rule. Here, the outermost function is natural log. So the derivative of natural log, normally it's 1 over x, but here it's going to be 1 over, again, whatever's inside it. Remember, the absolute value only affects the domain. It doesn't affect what it looks like, the derivative. It's just 1 over what's inside the natural log this time is the sine of e to the x. But then we have to multiply by the derivative of the next function inside is sine. And the derivative of sine, using the chain rule, is cosine. E to the x, the function inside stays the same. And since we have another function inside e to the x, we have to multiply by its derivative, e to the x. So there is just e to the x. So we could write it g prime of x equals e to the x cosine e to the x divided by sine e to the x. Well, let's suppose this was a multiple choice question on the AP test. And you did this correctly, but you don't see this answer anywhere as one of the choices. So what could they have done to write this in a different way, in a simpler way? Well, notice we've got cosine e to the x divided by sine e to the x. And remember, cosine divided by sine is the same as cotangent. So a simple way of writing this would be e to the x times the cotangent of e to the x. All right, let's take a look at a couple more derivative ones. So on this one, we're finding the derivative, f prime of x. We have e to the 3x times the natural log of cosine x. So overall here, since we have e to the x times the natural log of cosine x, big picture, we're going to be using the product rule. We have 2 functions multiplied together. But within each one of these, notice 3x is inside the function inside there, and cosine x is the function inside there. So we'll also need the chain rule as we go. So again, remember the product rule says we take the derivative of the first one times the second one as it is, plus the first one as it is, times the derivative of the second one. So let's start with the derivative of the first one. The derivative of e, remember, just stays the same when you take the derivative, so that e to the 3x stays the same. But using the chain rule, we have to multiply by the derivative of the function inside. The derivative of 3x is 3. So that's the derivative of the first one, times the second one as it is. So that one stays natural log of cosine x. And then plus the first one as it is. So that stays e to the 3x times the derivative of the second one. Again, this requires the chain rule. So you start on the outside. The derivative of natural log is 1 over whatever's inside of it, in this case cosine x. But again, we need the chain rule because there is a function inside. The derivative of cosine x is negative sine x. We multiply by that. And now let's just simplify this. Here, if you think of this again as your first term, plus this is your second term, what those have in common, you can take out as GCF as e to the 3x. And then let's see what's left of each term. Well, the first term we've got the 3 still. And we still have the natural log of cosine x. And then plus, well actually it was plus, but notice the derivative here was negative sine x. So this negative, this is all one term multiplied, we can bring out in front, actually changes it to be minus there. E to the 3x is gone, and then we'll have sine x over cosine x, which you could write that way, but a simple way, remember sine over cosine is the same as tangent. So that would be the simplified form of the derivative. All right, let's take a look at the next one here. Here it's y equals, so when we take the derivative, we let it as dy dx. Again, we've got a function inside, x squared plus e to the 5x, so we'll have to use the chain rule. And it's actually a double chain rule because there's also a 5x inside the e function, inside the exponent. So let's start on the outside with a natural log and work our way in. So the outermost function is natural log, so take the derivative of that. Normally it's 1 over x, but in this case it's 1 over whatever's inside of it, which in this case is x squared plus e to the 5x. And then work our way in. So the next function inside is x squared plus e to the 5x. So we multiply by its derivative, which is 2x, derivative of x squared, plus, then we need to use the chain rule again. The derivative of e to the 5x, the e part stays the same, e to the 5x, but there's a function inside that of 5x, so you use the chain rule now, we have to multiply it by the derivative of 5x, which is 5. And then you can write this as 2x plus 5 e to the 5x divided by x squared plus e to the 5x. So the question is it simplified further or not? Can we reduce the x's or the e to the 5x's? And the answer is no, because these are added together, right? You can't do that unless there's something you could factor out of these, and there's nothing that factors out of the numerator and denominator. If these are all just multiplied together, then you could reduce things, but since they're added, you can't do that. So that's as simple as it gets. All right. Now let's review a tangent line problem. This is write the equation for the tangent line to the function at the given x star. So things we've done earlier in previous lessons, but now using the new formulas we've just learned in this lesson. So remember the two things you need to write the tangent line are the point of tangency and the slope. So we already know the x coordinate of the point of tangency right here. To find the y coordinate, you just plug it into the function. So f of 1 would be 1 squared plus the natural log of 1 over e to the 3 times 1. Well, 1 squared is 1 plus the natural log of 1. Remember, that's a base of e. That's saying e to what exponent gives you 1. And the log is always equal to the exponent. Now, e to what exponent would be 1, that'd be e to the 0. The natural log of 1 is 0. And that's a common one they'll often ask you for, the natural log of 1 is 0. And then over e cubed. So that just simplifies to be 1 over e cubed. So that's our y-coordinate. So now we can see that 1 over e cubed, that's our point of tangency. Now we need the slope, and the slope comes from the derivative. So f prime of x, the derivative, that's where we'll have to use. Because we have this x squared plus natural log of x divided by e to the 3x, that's where we'll use the quotient. So remember the quotient rule, it's similar to the product rule, but not quite identical. You take the derivative of the numerator, times the denominator as it is, minus the numerator as it is, times the derivative of the denominator, all divided by the denominator squared. So let's start with the derivative of the numerator, which is 2x plus the derivative of natural log of x we learned is 1 over x. Make sure you put that in parentheses, because that whole thing is multiplied by the denominator as it is, which is e to the 3x. And then unlike the product rule, it's a minus instead of a plus. The numerator as it is, again in parentheses, x squared plus natural log of x. That whole thing times the derivative of the denominator. The e part stays the same, e to the 3x when you take the derivative, but we have to use the chain rule on that and multiply by the derivative of 3x, which is 3. And then don't forget it's all divided by the denominator as it is squared. So now you could simplify this. You could factor out e to the 3x, and it does simplify it, but that's fine. But you don't have to do that. In this case, we just need to know this gives you the derivative or slope at any point on the curve. But we want it specifically at our point of tangency when x is 1. So you don't want to simplify. You don't have to because you can just substitute in 1 right now. Or simplify first and then substitute in 1. Either way, you have to substitute in 1 at some point. So let's see what we get when we substitute in 1. Well, 2 times 1, that's just 2, plus 1 divided by 1 is 1. And then e, when you plug in 1 there, that's 1 times 3, that's going to be e cubed. Minus, you plug in there, 1 squared is 1, plus 1, the natural log of 1, remember we already figured out here, the natural log of 1 is 0. Times 3, then you plug in 1 there, that's e cubed. All divided by e, well 3 times 1 is 3, squared. And then when you have an exponent 3 to another exponent, you multiply the exponent, so that would be e to the 6. And let's just keep simplifying this. We get our slope of our tangent line, f prime of 1. Well, that's 2 plus 1 is 3, so we have 3 cubed. And then notice this is 1 times 3 cubed minus 3 cubed. Divided by e to the 6th. Well, 3 cubed minus 3 cubed, that's 0 over e to the 6th. So we get the slope of our tangent line is 0. So we ran into a special case here. If the slope is 0, well, what kind of a tangent line has a slope of 0? That's going to be a horizontal tangent line. Right? So we have something like this. So if you have a horizontal tangent line, well, what kind of an equation gives you a horizontal line? Remember, it's y equals. And what would y have to equal? Well, it has to go through our point of tangency here. So it has to have a y-coordinate equal to the y-coordinate of the point of tangency. So y would have to equal 1 over e cubed. That's the quickest way to get the tangent line equation in this case. But in general, what you would generally use point-slope form. So let's see what would happen if we did that. If we use point-slope form here, you'd get y minus the y-coordinate, 1 over e cubed, equals the slope, which we figured out is 0, times x minus the x-coordinate of the point of tangency is 1. But notice what would happen is 0 would wipe out the right side of the equation, right? And then if you just add over the 1 over e cubed, you'd end up with the same equation. So you could do it this way, just faster to go directly to it once a horizontal tangent line. All right, let's take a look at one more. This one, remember, when you have x's and y's all mixed up here, when this is not a function, this is where you use what's referred to as implicit differentiation in order to find the derivative. As opposed to when it's just y equals or a function equals, that's called explicit differentiation. So all the same rules for the derivative still apply, except because we're taking the derivative of the entire equation with respect to x, every time we take the derivative of a variable that's not x, in this case the y's, we'll have to multiply it by, in this case, dy dx. We don't have to do that on the x's because it'd just be dx dx, which would cancel out anyway. So, we take the derivative of 4x squared, that's just 8x, plus, when you take the derivative of x natural log of y, this is x times natural log of y, so yeah, that's going to require the product rule. Okay, so using the product rule, remember to take the derivative of the first one, with x, which is 1, times the second one as it is, natural log of y, plus the first one as it is, x, times the derivative of natural log of y, we learned is just 1 over y, but that's the first place where we took the derivative of a y term. So that's the first place we need to multiply that by dy dx. Then plus the derivative of e to the 2y, since there's a 2y up there, we'll have to use the chain rule on that. So the e part stays the same, but the derivative of 2y is 2. But again, we took the derivative of a y term, so again we have to multiply that by dy dx. Equals, the derivative of 4 is 0, and then the derivative of cosine of xy, well, we've got cosine on the outside, and inside that we've got xy, so overall it's the chain rule. So you start on the outside, the derivative of cosine is negative sine, so negative sine of xy. But the chain rule says we have to multiply this by the derivative of the function inside. But when you take the derivative of x times y, that's also going to require the product rule. It's x times y. So using the product rule on x times y, the derivative of x is 1 times y as it is, plus, first one as it is, x, times the derivative of y, is 1, but that's where we took the derivative of y term, so that's where we'll need dy dx. So that's our first step. But now we want to find dy dx, so we have to isolate it. And in this case, the thing that's going to make it difficult to isolate it right now is these parentheses right here. So to get rid of those, we can just distribute out the negative sign of xy. So I have negative sine xy, whoops, times y. Notice this doesn't become y squared. So y just goes out in front. And then minus x goes out in front times the sine of xy times dy dx. And on this side we can just leave all these terms alone. So 8x plus natural log of y, plus we can write this little letter as x over y times dy dx plus 2 e to the 2y times dy dx. Okay, and then remember the next step is we want to get, in order to isolate the dy dx, now that we got rid of those parentheses, we want to get all the terms that have dy dx on one side of the equation, all the terms that don't have dy dx on the other side of the equation. So you can choose either side. Since we already have two dy dx terms on this side, I'm just going to get all the dy dx's on the left. So I'll leave this x over y, dy dx on the left, and I'll also leave the 2 e to the 2y times dy dx on the left side. But then I need to move this term that has dy dx to the other side. Since it's negative, you'd have to add it to move it to the other side. So it'd be plus x sine of xy dy dx. And now we need all the terms that don't have dy dx on the other side. So the the terms that don't have dy dx, we'll leave this one over here. It's negative y sine of xy. But we also have to move the 8x, since it's positive, you have to subtract 8x to go to the other side. And also subtract the natural log of y. The reason why we do that is, remember, that allows us to factor out the dy dx out of these terms. So we all have dy dx. Okay. And once you factor out the dy dx, have it on the outside, then you can just divide by what's left. So I'm going to kind of do two steps in one here. So we factor out the dy dx and then divide by the terms that are left. So on the numerator, we'll have this. On this side, the negative y sine of xy minus 8x minus natural log of y. So it's going to be divided by, what we divide by is the x over y plus 2e to the 2y plus x sine of xy. And there's only one thing left to make it a little bit simpler. Normally we don't leave our final answer with a little fraction, smaller fraction inside of a bigger fraction there. So the way to get rid of that in one step is just multiply by the denominator of the little fraction, which is just y. So if you multiply the numerator and denominator by y, that will give us our derivative, dy dx. Y times negative y sine xy would be negative y squared sine of xy. Y times negative 8x would be negative 8xy. And then y times natural log of y, be careful there, it's not natural log of y squared. Just like a trig function, you can't multiply into what's inside the log of, so that this y has to go out front, minus y natural log of y. And all divided by. When you multiply this one by y, the y's cancel, that's when we multiply that to get rid of that little fraction, just leaving you with x plus, multiply 2e to the y times y, that becomes 2y, e to the 2y, and multiply this one by y, gives you plus xy sine of xy. And that concludes the notes for AP Calculus on the topic of differentiating, integrating, exponential, and logarithmic functions.